This lecture is going to be looking at section 5.3 out of the book. We're going to be picking up on the idea of similar matrices, and in fact looking at a very specific kind of similar matrices. Let's start by recalling the following problem. Remember when we were looking at using linear algebra for transitions? We had problems like this. That in any given year in a city, 15% of city dwellers move to the suburbs, 10% of suburb dwellers move to the city, and that there's no other change in the population. So we defined the variables where C is the city population at a given time and S is the suburban population at a given time. And we saw how to create these equations, where you're transitioning from year 0 to year 1, or more generally, transitioning from year K to year K plus 1. So remember we saw how to do these. Remember we also saw that if you want to project a few years into the future, how did you do it? Well, you started with your year 0. If you want to go n years into the future, so 10 years into the future, say, you would repeat your matrix 10 times, multiplying your matrix together 10 times to get your population 10 years in the future. Or writing it more compactly, you have your matrix raised to the n times your initial population is equal to your population that many years in the future. But what happens with large numbers of n? Like for instance, what's the population after 5 years? Or if you're talking even larger numbers, what's the population 30 years into the future? This becomes very complicated. Multiplying matrices together, when you're talking about running them on a computer or so forth, they are expensive. It's actually a fairly difficult problem to multiply matrices together. So what we're going to look at here is a way of kind of making a shortcut for this, a way of simplifying this using similar matrices. In fact, we're going to look at something called diagonalizable. So we're going to say a matrix is diagonalizable if there is an n by n matrix D, we should say where D is diagonal. So if there is an n by n matrix diagonal matrix D such that A equals P times D times P inverse for some invertible matrix P. In other words, A is similar to D. Okay, so we saw the idea of similar matrices. Now we're going to look at matrices that are similar to diagonal matrices, and we call them diagonal. And here's something to note. If you have something that's similar, A is similar to D, then A to the n is similar to P times D to the n times P inverse. Now why is that? Suppose we were looking at A to the n. Well, that's A times A times A times A. So that's equal to P times D times P inverse times P times D times P inverse, just over and over again, times P times D times P inverse, and you do that n times. So rewrite this now. You have P times D times, group these a little bit quickly, P inverse times P times D times, group the next ones, P inverse times P times D, and so on, all the way down, P inverse times P times D times P inverse at the end. But note now, this is identity, that's the identity, and so forth. So you can simplify this to say P times D times D times D, and so on, times D times P inverse. D is in there n times. So that's equal to P times D to the n times P inverse. Now, notice why is this so important? Well, I talked about briefly how it's difficult to take a matrix raised to a power. Multiplying matrices together over and over again is hard to do. It takes a long time, relatively speaking. But not when you have a diagonal matrix. Raising the power of a diagonal matrix is actually very easy. If D is an n by n diagonal matrix, and you want to take D to the n, so D times D times D times D, you just take the nth power of every diagonal entry. So for example, if that's D, what's D to the fifth? D to the fifth is equal to 3 to the 5 times 0 times 0 times 0 times negative 1, 0, negative 1 to the fifth, 0, 0, 2 to the fifth. And what are all these things equal to? Well, these are pretty easy to calculate. That's 243, 0, 0, 0, negative 1, 0, 0, 0, and finally 2 to the fifth is equal to 32. So see how fast and easy that is? Calculating powers of diagonal matrices is actually very easy. So with this in mind, let's pull together a couple of ideas that we've seen. Every n by n matrix A with n distinct L eigenvalues is diagonalizable. Okay, that's an important result. Furthermore, if we have this, we can find out exactly what our diagonal matrix D is and what our matrix P is. The matrix D, you take all the eigenvalues of A, put them along the diagonal, and put zeros everywhere else. There's your diagonal matrix. If you want to make P, go column by column. The first column of D is lambda 1. Take the eigenvector, that is the basis for that eigenspace, and make that the first column. Take your second eigenvalue, find the basis vector for that eigenvalue. That's your second column of P. And you just build P that way over and over again, one column for every eigenvalue, and that's the P that you're looking for. So here's an example. This is the matrix that we used for our initial problem. We're going to take this matrix and we're going to find a diagonal matrix for it. So first off, the first thing we want to do is we want to find the basis for each eigenspace. So we have to find the eigenvalues first. So to find D, we have to get the eigenvalues of A. Remember how to get the eigenvalues. We look for the determinant of D minus T times, of A minus T times the identity. So 0.85 minus T, 0.15, 0.10, 0.90 minus T. What's that equal to? Well, now we start solving this out. You're going to get 0.85 T, 0.85 minus T times 0.90 minus T minus 0.10 times 0.15. Figure this out. You are going to get 0.765 minus 1.75 T plus T squared minus 0.015, and of course we want this to be equal to 0. Simplify it a little bit. T squared minus 1.75 T plus 0.75 equals 0. You can factor this. You get T minus 1 times T minus 0.75 equals 0, which gives us our eigenvalues. Our first eigenvalue is 1. Our second eigenvalue is 0.75. Note that we have two eigenvalues, both with multiplicity 1. And as we're going to see, that is important because that tells us that we can find our diagonal matrix. We have two-dimensional, we have two eigenvalues, both with multiplicity 1. So now, this can give us, right away, we have our diagonal matrix. Our first eigenvalue and our second eigenvalue. There is our diagonal matrix. Our original matrix is similar to this one, and now we can use this information to find P. So to find P, we have to find each eigenspace. So our first eigenvalue is 1. Well, remember how to solve the eigenspaces? We have our matrix A minus 1 times I, and augment it. That's minus 0.15, 0.10, minus 0.10. Augment it with the zeros. Row reduce. We are going to get negative 0.15, 0.10, just by adding them together. Our last row is 0. And when we simplify it, we are going to get 1 2/3, 0, and 0, 0, 0. So there is our row reduced form. Now to get the basis, you can see we have one free variable. So we have x1 plus 2/3 x2 is 0, and x2 is our free variable. That leads to x1 is equal to negative 2/3 x2, x2 equals x2, and that tells us that our basis for our eigenspace is negative 2/3 and 1. Now for our second eigenvector, or eigenvalue. Again, we row reduce our matrix. This time when we subtract it, we get 0.10, 0.15, 0.10, 0.15, augmented with 0, 0. Row reduce, we're going to get 0.10, 0.10, 0, and a row of zeros, which becomes 1, 1, 0, and a row of zeros. Do the same thing, put it in general form. We have one free variable. Again, x2 is a free variable. So that leads to x1 is equal to negative x2, and x2 is our free variable. So our basis is negative 1 and 1. Now that gives us our P. So how do we get P? Well, we look back to D. D, first column of D had eigenvalue 1. So we take the elements, we take the basis for our eigenspace for that eigenvector. 2/3 and 1. There's our first column. Our second column of D is 0.75. So we look at our eigenvalue 0.75, take the basis element for that, negative 1 and 1, and there is our P. So this gives us the value of P, where A is equal to P times D times P inverse. And you can check this. So if you're doing this problem, you can check it out and just multiply and see that they're the same. But actually, there's even another simplification for checking it, because what happens if you multiply both sides of this by P? That gives us A times P is equal to P times D. So at this point, if you know A, you know P, and you know D, and you want to just double check your calculations, just do those multiplications. Make sure they come out to the same thing. If they do, you've got it right. So returning to the problem we started with, remember this was all about simplifying it and noting that calculating this matrix to the fifth or to an even larger number is a difficult problem. But now we found that this matrix is similar to our diagonal matrix using our P and D. So when we write it all out, we get our, what we're looking for, C5S5, is our matrix P times our diagonal matrix raised to the 5th times our P inverse times our initial population. Now, we do have to figure out the inverse for this, and we do have a couple of matrix multiplications, but especially going to the 5 isn't too bad, but if you were raising this to the 30th, this is a much easier calculation than raising a matrix to the 30th, because raising a diagonal matrix to a power is a very easy operation. There's the matrix raised to the power. Now we just have a couple of matrix multiplications to do to come up with our answer. So, diagonal matrices, or similar matrices, diagonalizable matrices in particular, often give us a way of solving problems easier because it is computationally expensive. It's a lot of work to multiply matrices together. Multiplying diagonal matrices together is very, very easy. So it's a way of making problems easier. And that leads us to a couple of theorems. So the first theorem is essentially summing up what we've just done. A matrix is diagonalizable if and only if there is a basis for Rn consisting of eigenvectors of A. So the situation we had was that all of our eigenvalues have multiplicity 1. Well, in that case, we do have that it has eigenvectors of A. Furthermore, we have A equals P inverse D times P, where D is a diagonal matrix and P is the columns for our basis. Okay, so that's just what we've just done, just putting it into a theorem. Theorem 5.3 says that if we have eigenvectors of a square matrix that correspond to distinct eigenvalues, then it's linearly independent. So in other words, that matrix P that we built this way, it is a linearly, the columns are linearly independent. Again, pulling in some ideas from earlier classes, if our matrix is invertible, its columns are linearly independent. And out of this, we get a test for a diagonalizable matrix whose characteristic polynomial is known. So in other words, if you know the characteristic polynomial of a matrix, you can see from it whether or not it is diagonalizable. This is a little more general than what we just did, but these are the rules for seeing if your matrix is diagonalizable, because not every matrix is. Even if you can calculate your eigenvalues, it's not always diagonalizable. Only some of them are. This is the test for seeing if you can simplify it to a diagonal matrix. There are two conditions that have to be met. First is that the total number of eigenvalues of A, when each eigenvalue is counted as often as its multiplicity, is equal to n. So take all the eigenvalues, take all the multiplicities, add them all up, and if that's equal to the number of rows in your matrix, you've met your first condition. The second one says that for each eigenvalue, the dimension of the corresponding eigenspace is equal to the multiplicity. So remember we said when we had something like multiplicity 3, that the dimension of the eigenspace could be 1, 2, or 3. To be diagonalizable, it has to be 3. If it's 1 or 2, right away you are not diagonalizable. The dimension of your eigenspace has to be equal to the multiplicity, and all of those multiplicities have to add up to the number of rows in your matrix. So let's finish this off by looking at a couple more examples. So here I'm going to give you the characteristic polynomial just to make it a little bit easier. Is this diagonalizable? If so, let's find D and P. So we can see from this, from our characteristic polynomial, we can get our eigenvalues. So our eigenvalues are lambda 1 is equal to 6. It has multiplicity 1. Our second eigenvalue, lambda 2, is equal to negative 2. It has multiplicity 1. Add up the it has multiplicity 2 because it's squared. Add up the multiplicities. We have 3. So we meet our first condition. So we've met our first condition. Now we have to see if the dimension of our eigenspaces is equal to the multiplicity in both cases. So we have to find the basis for our eigenspaces. So let's start off with our first one. So our basis for lambda 1 equals 6. When we take our a minus 6 times I, we're going to get 0, negative 8, 8, negative 4, negative 4, negative 4, and negative 4, 4, minus 6 is equal to minus 12. Augmented with 0, 0, 0, and start row reducing. And I'm going to save time here. You can row reduce it. But when you row reduce it, you end up with this. 0, 1, 0, 0, 1, 0, 0, 0, 0. So there is our row reduced form. And we can get from this that the basis is equal to, again, by using your free variables. I'm jumping ahead a little bit, but that's our basis for our first eigenspace. So this is multiplicity 1. We have one basis member. We're good there. Now we have to check the second one. So what about our second one? So our second one is lambda 2 equals negative 2. This has multiplicity 2. But what is our basis? So take a minus negative 2 times I. We end up with 8, negative 8, 8, negative 4, 4, negative 4, and negative 4, 4, negative 4, augmented with the zeros. Again, go through all the row reductions. And as a shortcut, when we do all the row reductions, you are going to end up with 1, negative 1 half, 1 half, 0, and the other two rows are 0. When you have two free variables here, so when you work it out, you end up with the basis being equal to 1 half, 1, 0, and negative 1 half. Sorry. This is negative 1 half up here. The second basis element is 1 half, 0, 1. So our basis has dimension 2. Our eigenvalue had dimension 2. So that all matches up. So this tells us that we are diagonalizable. Now, what is our diagonal matrix equal to? It's equal to, well, our first eigenvalue was 6 with multiplicity 1. Our second eigenvalue is negative 2 with multiplicity 2. So there's our D. Our matrix P is equal to, well, you just put in your the basis for your eigenspace for 6, and then for negative 2, we have two columns, we have two basis vectors. We put in the two basis vectors, and there is our matrix P. So again, we are diagonalizable. And here is our diagonal matrix and our matrix P. One more final example. We have this characteristic polynomial. What do we have here? So we want to see if this is diagonalizable. This gives us lambda 1 is equal to 1. But this, you don't have numbers for that. You need complex numbers for that. So you don't have real numbers for that. So this has no solution. So for this problem, we have only one eigenvalue of multiplicity 1. It doesn't add up to, we have 3 dimensions here. It doesn't add up to 3. So A is not diagonalizable. Okay. So that's the first example we saw of something that wasn't diagonalizable. And in fact, it's the first example we saw of something where you can't get all of your eigenvalues. That happens sometimes. So here are some practice problems for section 5.